Just before we start doing our example, there's one more thing that we need to notice. So you remember that the definition of the complex exponential e to the I theta was cos theta plus I sine theta. So e to the I n theta is just cos n theta plus I sine n theta. And if you think about this in terms of the real and imaginary parts, this is the real part of the complex number and this is the imaginary part of the complex number. So that's what we've got here. Cos n theta is the real part of e to the I n theta and sine theta is the imaginary part of e to the I n theta. Okay, so we're going to put a couple of ideas together now to answer this question. So we want to use the complex exponential and De Moivre's theorem to express sine 3 theta in terms of sine theta only. So we want to change the argument here from 3 theta to theta. So I've just written this from the previous page. So in terms of our real and imaginary parts, sine 3 theta is equal to the imaginary part of e to the I 3 theta. But e to the I 3 theta is just equal to e to the I theta cubed. And I know that because that's the result from De Moivre's theorem. Okay, and so let me just expand out the bracket now. So e to the I theta is cos theta plus I sine theta cubed. Now what I have is a term that looks like a plus b cubed, and we can expand that using the binomial expansion. So what did it say we had to do? It said we took the first term to that power. So it was cos cubed theta. Then we had cos squared theta times this term. So that's times I sine theta. Then we had this term cos theta times this term squared, so I sine theta squared. And then we had the last term cubed. Okay, and the only thing we need to do is figure out what the coefficients were, and if you go back to look at your page on Pascal's triangle, you'll find that this term has a coefficient of 1, this one has a coefficient of 3, so does this one, and the last term has a coefficient of 1. So let's expand these terms now. We get cos cubed theta plus 3 cos squared theta I sine theta, and I've got a squared term here, so the I is squared, so that becomes minus 1, or we'll just bring the minus sign out the front, so we get minus 3 cos theta minus 3 cos theta sine squared theta plus, I've got an I cubed now, so that's a minus I sine cubed theta. So that's what that looks like when we use the binomial expansion. But when we go back up here, remember what we said was that sine 3 theta equals the imaginary part of e to the I 3 theta. So we're using this result now. So if we want to write sine 3 theta, so we're looking for the terms here that have got I in their product. So this one doesn't include an I, so that's the real part of the complex number. This one has an I, so 3 cos squared theta sine theta is in the imaginary part of the complex number. This one is a real number, it doesn't have any i's in there, but this one does. So it's minus sine cube theta. So the imaginary part of e to the I3 theta is 3 cos squared theta sine theta minus sine cube theta. Okay, well I'm almost there but not quite, because what I was asked to do was write sine 3 theta in terms of sine theta. And I'm almost there, but I've got a cos squared term and I don't want that. So I'm going to use the Pythagorean identity. So cos squared theta equals 1 minus sine squared theta. And I'm going to substitute this expression for cos squared theta. So this is 3, 1 minus sine squared theta times sine theta minus sine cube theta. So this is 3 sine theta minus 3 sine cube theta minus sine cube theta. So that's 3 sine theta minus 4 sine cubed theta. And I'm done. So when we're thinking about expressing cos theta and sine theta in terms of the complex exponential, we can do that in another way. So we're going to have a look at that now. So again, we're starting off with this basic definition of the complex exponential, and we're going to use these two properties, and I think we talked about them earlier in the course. Cos theta is an even function. So that means that cos theta is equal to cos of minus theta. And remember, I talked about that earlier. Think about the graph of cos theta. This just means when you've got an even function that if you've got x and you look at its y value, it's the same as the y value for minus x. So it's like reflecting the functions of the graphs reflected across the y-axis. So that's what's going on here. So it's an even function. On the other hand, sine theta is an odd function. So that means that sine of minus theta equals minus sine of theta. And if you think about the graph of sine, so if you take this x value, you get y. If you take minus x, you get minus y. So it's not reflected across the y-axis alone. You've got to reflect it across the y-axis and then reflect it across the x-axis as well. So these two properties we're going to use to write, instead of e to the I theta, we're going to write e to the minus I theta. So e to the minus I theta is just equal to cos of minus theta plus I sine of minus theta. But cos of minus theta we said was just cos theta, and sine of minus theta is minus sine of theta. So when we look at the complex exponential for minus I theta, we get cos theta minus I sine theta. If we write out e to the I theta plus e to the minus I theta in full, e to the I theta is this expression, and e to the minus I theta we just figured out looked like that, and we add those two things up, we get 2 cos theta, but the imaginary parts cancel out because I've got I sine theta minus I sine theta. So if we add up e to the I theta plus e to the minus I theta, we get 2 cos theta. And then if I rearrange that in terms of cos theta, we see that cos theta equals a half e to the I theta plus e to the minus I theta. Okay. If instead we take e to the I theta minus e to the minus I theta, then what we get is, well, let me just do it up here. That becomes a minus sign for this expression, and so I get now cos theta minus cos theta, so that's 0, and I sine theta minus I sine theta, so that gives me 2I sine theta. And then if I rearrange that in terms of sine theta, I get 1 over 2I e to the I theta minus e to the minus I theta. And now we can use these different identities to find expressions for powers of cos or sine. All right, so I'm going to get you started on this one, but then I'm going to leave you to finish it off for yourself. So we want to express sine to the fourth of theta as the sum of sines or cosines of multiples of theta. Okay, so let's think about how we might do that. So first up, we've got sine to the fourth of theta, and I'm going to write that as sine of theta to the power 4. That's just the same thing. And then I'm going to use one of the expressions that we just developed. So we said that sine of theta was 1 over 2i e to the I theta minus e to the minus I theta. So that's sine theta, and that's raised to the power 4. So you can see that I've got this term at the front, so this is 1 over 2i to the power 4 times e to the I theta minus e to the minus I theta to the power 4. And now I'm going to let you try and finish this off. Remember that this is something that looks like x plus y to the n, so you can use the binomial expansion. Be a bit careful with the minus sign. If you've got x minus y to the n, then you can write this as x plus minus y to the n. So your term, you leave the plus in the middle, but your term becomes a negative term. So take that into consideration with your calculation and see how you go, and we'll have a look at this in class on Tuesday or Thursday next week. Okay, so where are we at? Well, I think we've got pretty much to the end. Got some blank pages there for you to write on, but pretty much to the end of this section. So in topic 3, you can do problems 16 to 17 and 23 to 24. Some of these calculations get a little bit complicated, so you might want to do a couple of examples just so you've got the technique under your belt. And then in our next video, we'll be looking at roots of polynomials. Okay, so I'll see you next week. Bye.